Probability trees, section 3.4. Example 4. A test had been developed to detect a certain type of cancer. The test correctly identifies 95% of cancerous people as cancerous and correctly identifies 80% of non-cancerous people as non-cancerous. It is known that 0.2% of the population has this type of cancer. We want to answer two questions here. Given that the test indicates a person has cancer, what is the probability the person actually has the cancer? And part B, given the test indicates the person does not have a cancer, what is the probability the person actually does not have cancer? So the original probabilities were given 95% and 8%, 80% are probabilities that come from testing the test. So for those percentages, it is known whether the person has cancer or not, and you're just trying to test the test by testing that person. But in a clinical situation, so that would be like in a research situation. In a clinical situation, you don't know whether the person has cancer, but you know the results of the test. So we're given conditional probabilities here, and we want to reverse those conditional probabilities. So we're going to make a tree. The numbers we're going to put in the tree, the probability of cancer is 0.2%, which is a decimal. You have to divide by 100, 0.002. Probability of no cancer is 1 minus 0.002 is 0.998. And the conditional probability of testing cancer, if the patient has cancer, 95% or 0.95. Probability of testing says no cancer, if the patient has cancer, would be 1 minus 0.95 is 0.05. Probability the test says no cancer, if the patient has no cancer, that's given, 80% or 0.8. Probability the test says cancer, if the patient has no cancer, 1 minus 0.8, 0.2. And we can use those numbers to fill in the tree. So we start with either the patient has cancer or does not, and the probabilities are 0.002 and 0.998. And then either the test says they have cancer or the test says they don't have cancer. So 95% of the time, if the patient has cancer, the test will say the patient has cancer. 5% of the time, the test will say not. So, and we want to multiply across to get the intersection. So 0.02 times 0.95 is 0.0019. That's the probability of the patient has cancer and the test says cancer. 0.002 times 0.05, 0.0001, that's the probability the patient has cancer and the test says no cancer. And then the third path, we have the probability that the patient doesn't have cancer is 0.998, there's a 2.2 chance that the test will say cancer even though the patient has no cancer. 0.998 times 0.2, 0.1996. That's the probability of patient has no cancer but the test says cancer. And then 0.998 times 0.8, that's the probability patient doesn't have cancer and the test says no cancer. That's 0.7984. So our sample space would be these four possible outcomes. Cancer and test cancer, cancer and test no cancer, no cancer and test cancer, no cancer and test no cancer. And now we can answer the questions. For part A, the probability of cancer if the test says cancer. So that there's one path where so that's going to be the quotient, the probability of cancer and the test says cancer divided by the probability of the test says cancer. Well, there's one path here, that's the 0.0019, where the patient has cancer and the test says cancer. And then there's two paths where the test says cancer. This is the 0.0019, 0.0019 and the 0.1996 are the two paths where the test says cancer. So that's going to be our denominator. And if we divide, we get 0.009. So that could be very disturbing. That's what's called a false positive. So there's if the patient if the test says cancer, there's only a small percent chance that the patient actually has cancer. So you wouldn't want to use this test by itself. Maybe use it in combination with other tests or other diagnostic tools. But it could be very disturbing to a patient if the test says they have cancer, and in this case, a lot of times, for this particular example, the test would usually be wrong in that instance. So it could cause some unnecessary anxiety. Part B, probability of no cancer. If the test says no cancer, it's probability of no cancer and test says no cancer divided by the probability of test says no cancer. And there's only one path where the patient has no cancer and the test says no cancer. That's the 0.7984. And then there's two paths where the test says no cancer. That's the 0.0001 and the 0.7984. So the denominator, want to add those two. So this comes out to be 0.99987. This is very close to 1. So the test is good for in this kind of situation, if the patient doesn't have cancer, if sort of reassuring them that it's very likely that they don't have cancer. Okay, so for this, we use a tree here to reverse conditional probabilities, and these reverse conditional probabilities are called posterior probabilities. There's a theorem, Bayes' theorem, that actually gives a formula for computing these. However, I would like you to use trees. The formula, I think, the trees help you give you more of an intuitive understanding of what's going on. We're going to have a lot of formulas already in this course without adding Bayes' theorem to the list of formulas. Sometimes plugging into formulas doesn't really give you a sense of what's really going on. Okay, so anyway, that concludes this presentation.